Imagine playing a game with your friend where you both have identical looking candies, one tasting sweet and the other tasting very sour, and both of you will be tasting the candies in a vast distance. Whoever gets to pick the sour one loses. So you both have 50% to pick the sour one or the sweet one. Now, as you both tasted your candies, you felt relieved after only tasting sweetness, which means you're 100% sure, no matter your distance from each other, that your friend definitely had the sour one. This 50-50 situation only depicted that both of your candies were intertwined in a certain way. This makes you wonder, how can a silly little game ever be related to quantum physics? Well, in the teeny tiny world of atoms, something similar happens. They can be like those two candies. When we do something to one particle, its partner, no matter how far away it is, feels it instantly. Scientists call this quantum entanglement. It's like they have a super duper special connection that lets them share secrets in a way we can't even imagine. This might sound impossible, but it's exactly what quantum entanglement does to individual particles in experiments. This concept of quantum entanglement occurs when two particles, such as a pair of photons or electrons, become entangled. They will always remain connected even when separated by limitless distances. Consider carefully preparing two particles to become entangled in a lab, ensuring they will have opposite spins. Line up opposite to one another in a magnetic field is one way to arrange this. The spin of one of the particles is then measured after thousands of kilometers have separated the particles. The others will always point down if you notice that one spin is pointing up. Similar to the candy example, you will instantly know that your friend's particle has spun down and vice versa whenever you measure the spin of the particle. Or, as Isaac Newton called it, spooky action at a distance. According to his theory of relativity, no information can move faster than the speed of light. Entanglement, however, seems to imprison this concept inside an airlock. The state of the entangled particle in your possession is random, just like in that ridiculous little game. You can't predict whether something will be sweet or sour in advance. You only know the other particle will be the opposite when you measure it. No one knows if any scientific theory is right or wrong until said theory can be tested and proved.